What if the computers we use today are just the warm-up act? From your smartphone to supercomputers, all follow classical physics. But there's a new contender, quantum computers, which don't play by those rules. They don't just process information, they redefine what information even is. So, could they really mark the end of silicon? Let's dive into the physics, limits of current tech, and how close we are to quantum machines taking over. For nearly 80 years, classical computers used silicon transistors, tiny on or off switches, 1 or 0. This binary language forms modern computing. We've shrunk transistors to atomic scales. Advanced chips pack hundreds of billions, each smaller than a virus particle. But we're running out of room. When a transistor is just a few atoms wide, quantum effects leak in. Electrons tunnel, bits flip randomly, and heat skyrockets. Silicon, computing's foundation, is reaching its physical limit. Instead of fighting quantum physics, what if we used it? A quantum computer uses qubits, not bits. A qubit can be both 1 and 0 simultaneously, a state called superposition. Imagine a coin. Classically, it's heads or tails. Quantically, it's both until observed. Then there's entanglement. Qubits link, so changing one instantly affects another, even miles apart. Einstein called it spooky action at a distance. For computation, it means qubits work as one massive, interconnected system. Classical computing adds power linearly. Quantum computing adds power exponentially with more qubits. Quantum computers use fragile systems like superconducting loops, trapped ions, or photons for qubits. These qubits are so sensitive that vibration or heat can destroy their quantum state, a process called decoherence. That's why they operate near absolute zero, colder than outer space. Scientists use quantum gates, like laser pulses or microwave radiation, to manipulate qubits for computation. The result is a probability landscape of answers. When measured, qubits collapse into the most likely solution. It's probabilistic, not deterministic, which is both the beauty and challenge of quantum computing. Quantum computers excel at problems involving massive combinations and probabilities. Problems taking classical supercomputers billions of years, quantum machines could do in minutes. For example, simulating molecules for new drugs or materials. Optimizing logistics, like airline routes or financial portfolios. Breaking encryption. Shor's algorithm on a powerful quantum computer could crack RSA, which protects internet data. Governments and companies are racing to develop quantum-safe encryption. Not quite. Quantum computers are still noisy and make errors. A useful quantum machine needs millions of qubits, but current systems have hundreds at most. However, we're in the era of quantum advantage, where small quantum processors outperform classical ones in specific tasks. In 2019, Google performed a calculation in 200 seconds that would take a supercomputer 10,000 years. It was a narrow case, but showed potential, and progress has accelerated since. IBM, Intel, Google, IonQ, and Rigetti are building better qubits, algorithms, and systems. So, is this the end of silicon? Not yet. Quantum and classical computing will coexist for a long time. Quantum computers won't replace your laptop. They'll work alongside classical machines for problems silicon can't handle. One handles general logic, the other tackles parallel, high-complexity calculations. Think of it like the relationship between a CPU and a GPU. Quantum will be the third layer, a QPU, for the world's hardest problems. Some predict quantum cloud services, where you rent time on a quantum processor through companies like Amazon Breakit or IBM Quantum. We're in the pre-industrial age of quantum technology, like computers in the 1950s. Huge, expensive, delicate, but improving fast. By the 2030s, experts expect error-corrected quantum systems with thousands of stable qubits. By the 2040s, they could transform medicine, AI, materials science, and weather prediction. Just as silicon microchips reshaped the 20th century, quantum information could reshape the 21st. The irony is, pushing computing limits forces us to confront nature's laws. To move beyond silicon, we must speak the language of the universe, quantum mechanics. The next revolution won't be bigger screens or faster chips, but mastering the invisible, probabilistic, entangled reality hidden from us. The quantum world isn't science fiction. It's the next frontier of human ingenuity. Thanks for watching. If you enjoyed this deep dive, like, subscribe, and share it with anyone curious about computing's future.